Welcome to Signals and Systems subject classes. Now we are in the fifth chapter, that is continuous time Fourier transform. So in this chapter, so this is the third video. In this video, we are going to start properties of the continuous time Fourier transform. Properties of the continuous time Fourier transform. You know, we studied the properties in the continuous time Fourier series and discrete time Fourier series. So before entering into the properties of the continuous time Fourier transform, I would like to write the formulas for the continuous time Fourier transform and the inverse Fourier transform formula. So this x of t, it is a continuous time. X of t is continuous time signal. It is not periodic, it is a periodic signal. You know that Fourier transform, it is applicable for the aperiodic. Means Fourier transform, it is also applicable for the periodic also. The aperiodic is a special case. So it's Fourier transform. No, this is x of t. So Fourier transform. So CT of t. Continuous time Fourier transform, that is denoted by the x of j omega. We derived the formula for x of j omega, and x of t is, it is from the x of t to the x of j omega, it is called continuous Fourier transform. From the x of j omega to the x of t, it is the inverse Fourier transform. The formula for the Fourier transform, that is x of j omega equal to integral of minus infinite to the plus infinite x of t into e power minus j omega t into dt. So inverse Fourier transform, so that is equal to x of t. So x of t equal to 1 by 2 pi integral of minus infinite to the plus infinite x of j omega into e power j omega t into d omega. So here we are doing the integration with respect to t. Here we are doing the integration with respect to omega. The first property is the linearity. So you know that to prove the linearity, we need to take the two signals. So that is for the x of t, its Fourier transform is x of j omega, and y of t, its Fourier transform y of j omega. So to satisfy the linearity, it should satisfy the additivity and scaling property. So scaling property, so x of t must be multiplied by the one constant, that is I have taken the a plus b into y of t. So this plus it is for the checking the additivity property. This A constant multiplication, it is for the scaling property. So this it is follows the linearity. So Fourier transform. So that equal to A into x of j omega plus B into y of j omega. So this is the linearity. The second one is, it's very, very important. That is time shifting property. So for the time shifting property, so for example, x of t, we're taking one x of t. So this is a reference signal. Why I'm taking only x of t? So this is a reference x of j omega. So now apply the time shifting transformation to the x of t. You take delay or advance anything. So I'm taking the delayed signal x of t minus t naught. So this is the delayed signal of the x of t by the t naught units. Then for that, what is the Fourier transform? So that is the question. To derive this one, simple. So here this is x of t, is it? So x of t, just replace the t by the t minus t naught. Then you will get corresponding signal in the frequency. So this is x of t, its corresponding signal in the x of j omega. So the form, so it must be multiplied by e power j omega. For this concept only, this formula, x of j omega considered as a frequency domain signal to the x of t. So just replace the t by the t minus t naught in that equation. So here I'm writing. So that is so x of t equal to 1 by 2 pi integral of, so minus infinite to plus infinite, x of j omega into e power j omega t into d omega. So just replace the t by the t minus t naught. Just substitute t minus t naught in place of the t. 1 by 2 pi integral of minus infinite to plus infinite x of j omega into e power j omega into t minus t naught into d omega. So 1 by 2 pi, so minus infinite to plus infinite x of j omega e power j omega t. You should write a formula similar to this one. So e power j omega t into e power minus j omega into t naught into d omega. So I'm writing in the form of something x of j omega into e power j omega t. So that's why, so here I'm writing x of j omega into e power minus j omega t naught. So this is, so this is the formula for the x of t minus t naught. So what did you understand? This is the, see, x of t equal to 1 by 2 pi something function into e power j omega, something into e power j omega t. So this is the signal in frequency domain corresponding this x of t minus t naught. So x of t minus t naught, then the signal in the frequency domain, that is must be multiplied by the exponent signal, that is e power minus j omega into t naught. And note, for the advanced case, for example, advanced x of t plus t naught, for that case, the Fourier transform x of j omega into e power j omega into t naught. So this is for the advanced signal. This is for the delayed. Both are comes under the time shifting property. Next property, so that is third one, frequency shifting. Frequency shifting property. So x of t x of j omega, it's Fourier transform. Then what is the time domain signal for the shifting in the frequency domain, that is omega naught? What is the corresponding signal in time domain? For the case, I am taking the Fourier transform formula. So x of j omega, so that equal to integral minus infinite to plus infinite. So x of t into e power j omega t into dt. Just replace the omega by the omega minus omega naught. J into omega minus omega naught. So this is x of t into e power minus j, replace the omega by the omega minus omega naught. So omega naught is a constant, omega is a variable here, into dt. Expand that one. So minus infinite to the plus infinite. So x of t into e power minus j omega t into e power minus into minus plus, so that equal j omega omega naught into t into dt. Here I'm writing like this. So minus infinite to plus infinite. So x of t, so this is a signal in the time, is it? But that exponential must be function of the only t. So this is the function of the t only. E power minus j omega into dt. So this is equal to the x of omega minus omega naught. So this is a signal in frequency. This is a signal in the time domain, is it? X of t. So for the delayed in the frequency, it is equal to the x of t into e power j omega. So x of t must be multiplied by the e power j omega naught t. So that here you can write x of t. So x of t into e power j into omega naught into t. So in frequency domain, for the delay, the signal must be multiplied by the positive. In time domain, for delay, x of j omega must be multiplied by the minus exponential. So that is a difference. Here also we can write some note. So the note, that is nothing but for the x of J of omega plus omega naught. That's signal in time domain that equal to x of t into e power minus j omega naught into t. So this is all, it is a function of the t only. There is no omega variable. This is Fourier transform. The fourth one, complex conjugation. Complex conjugation. So this is x of t continuous time Fourier transform that equal to x of j omega. Then if you take the complex conjugate in time domain, then what will happen in the frequency domain? Okay, in this case, I would like to prove that. So for that, to prove the x of t complex conjugate, we should take the x of t signal. So x of t that equal to 1 by 2 pi integral minus infinite plus infinite. So x of j omega into e power j omega t into d omega. So now I'm taking the complex conjugation operation on both sides. So both sides. So this 1 by 2 pi is a constant. So this is a real number. So there is no change. So minus infinite to plus infinite. So x of j omega. So x of j omega complex conjugation into e power j omega t complex conjugation into d omega. So this is a complex. We don't know x of j omega whether it is a real or pure complex or purely complex. We cannot take the decision. So for this is the complex number. So then automatically sign will be changed. So for that case, 2 pi integral minus infinite to the plus infinite. So, so here x of j omega complex and apply the complex conjugation. So that equal to minus j omega t into d omega. So here the sign of the omega is changed. So here I'm writing like this. So 1 by 2 pi integral of minus infinite to the plus infinite. So I'm changing the omega that equal to minus j omega into e power j omega t into d omega. This is the so x of t complex conjugation. So that equal to x of j omega x of minus j omega complex conjugation. So this is the frequencies. domain signal. So x of minus j omega. So next property, time reversal. Or fifth one. So that is time reversal property. So time reversal. So x of t is x of j omega. So x of minus t Fourier transform. So that equal to x of minus j omega. So easily we will get use the formula. So time scaling. So this x of t Fourier transform is x of t x of j omega. So x of a into t, it's Fourier transform. So that equal to what? So we know that x of j omega equal to integral x of t into e power minus j omega t into dt. So this is minus infinite to plus infinite. Now I'm going to substitute. It is x of at in place of the x of t. Then I will get the signal in the frequency domain corresponding that. So x of at into e power minus j omega t into dt. So here I am taking the at. I'm going to change the variable. So at here I am assuming tau. So dt equal to d tau by a. So changing the variable. So integral minus infinite to plus infinite. So x of tau into e power minus j omega. So what is the t here? T equal to tau by a. So tau by a. I am taking to the frequency into d tau equal to d tau by a. So here I am taking the mod of a integral minus infinite to plus infinite. So x of tau into e power minus j. So here the omega in omega place, omega by a, it is in the place of the omega into d tau. So this is the constant. So this is, so you should write omega by a in place of the omega. So the corresponding signal is, so x of, so 1 by a, so this 1 by mod a integral of, so minus into plus infinitive, so x of tau into e power minus j omega by a tau into d tau. So 1 by mod a. So in the place, so x of j. What is the omega here? Omega by a. So this is the answer. So here answer 1 by mod a x of j omega by a. So this is a very, very important property. Time shifting and time scaling. This is very, very important. Time scaling property. The seventh one is convolution. It is also important. So convolution. So convolution in the time domain. You know, x of t Fourier transform is x of j omega and y of t its Fourier transform is Fourier transform and its Fourier transform that equal to y of. So convolution in the time domain, the corresponding in the frequency domain is multiplication. So Fourier transform that equal to x of j omega y of j omega. So very, very important this convolution. Time shifting and time scaling and convolution. These three are very, very important. The next one is multiplication. So multiplication. So multiplication in the time domain, the corresponding the frequency domain, that is the convolution. Fourier transform that equal to x of j omega convolution y of j omega. So what is the to write this convolution integral x of j theta into y into j into omega minus theta into d theta from minus infinite to plus infinite. This is the convolution formula. So the ninth property, differentiation. Differentiation in time domain. So x of t that is x of j omega, then so d by dt of x of t is what? So this is Fourier transform. For this case, to prove this one, I'm taking the inverse Fourier transform. So inverse Fourier transform, that is so x of t, so that equal to, so 1 by 2 pi. So integral of minus infinite to plus infinite. So x of j omega into e power j omega t into d omega. So now I'm differentiating on the both side. So d by dt of x of t that equal to 1 by 2 pi. So differentiate. So already here we have the integration. if you want to do the integration, so differentiation in the integration, so it becomes the partial differentiation. So partial differentiation with respect to t, this is the constant. So leave it. Then, so partial differentiation. So dou by dou t of e power j omega t into d omega. So this is why we leave this one. So why? Because this is a partial differentiation with respect to t. This is a constant. So differentiation. So for that case, 2 pi integral minus infinite to plus infinite x of j omega to do the differentiation. So j omega t. So we're doing the with respect to t. So j omega, it is a constant. So what we are getting? So 1 by 2 pi integral of, so minus infinite to the plus infinite. So x of j omega into j omega. So this is the frequency domain signal into e power, so d omega, e power j omega t into d omega. So this is d by dt of x of t signal. So d by dt x of t and x of j omega, these are the Fourier transform pairs. So yeah, so we are getting j omega into x of j omega. The next property, integration. Integration property. So here directly I am writing same concept. So x of t is x of j omega. So integral of, so x of tau into d tau minus infinity to t. So that equal to, so generally we will get the x of j omega by j omega, and also we are in the integration we should write constant. That constant equal to pi into x of 0 into del of omega. So this is the property. The next property, so differentiation. Now differentiation in the frequency domain. Differentiation in frequency domain. So that equal to, so x of t, so its Fourier transform. So its Fourier transform is x of j omega. Then so d by d omega into x of j omega is what? For that, here we are doing the differentiation to the x of j omega. For that case, here I am taking the Fourier transform that equal to integral minus infinite to the plus infinite. So x of t into e power minus j omega t into dt. So now differentiate with respect to omega. So x of j omega again, so minus infinite to plus infinite. So partial differentiation with respect to omega. So x of t is a constant. So partial differentiation, so minus j omega t. So partial differentiation with respect to omega. So the constant is minus j into t. Must be multiplied into dt. So what is the signal here? So minus infinite to the plus infinite. So here we are getting the minus j x of t into t into e power minus j omega t into dt. This is d by d omega x of j omega. So d by d omega omega x of j omega, its inverse Fourier transform equal to minus j x of t into t. Here, so this is a constant. Minus j is a constant. We can send to the left side. I want to send to the left side. So 1 by, so minus, so minus 1 by j here, minus 1 by j, that equal to j. So 1 minus 1 by j is nothing but j. So j into, so d by d omega x of j omega equal to minus infinite to the plus infinite t into x of t into e power minus j omega t into dt. So these are the Fourier transform pairs. So we can write here this. So this is, we can write this is j and t into x of t. So this is very important property. So very important. This one and this one and this integration property. So next 12th one, conjugate symmetry, same similar to the Fourier series. Conjugate symmetry. So already this is the third time same concept, but just to write the x of j omega only. And previously we have taken the x of ak. So here we just write x of j omega in place of the ak. So here x of t, it is a real. So then real. So this x of minus j omega complex conjugate, it becomes it equal to the x of j omega. So this is the case. So the real part of, so real part of x of j omega equal to real part of x of minus j omega. Imaginary part of x of j omega, that equal to minus imaginary part of x of minus j omega. The mod of the x of j omega equal to mod of the x of minus j omega. But angle is different. Phase of the x of j omega, it is equal to the minus phase value of the x of minus j omega. So these are the very important. You may expect the question from this concept. So be careful. Once you learn here, same concept, you can apply the continuous time Fourier series and discrete time Fourier series. In even discrete time Fourier transform also same concept. So next 13, real and even. So real and even for this signals, real and signal. So now our signal is real. X of t is real and even. Then the x of j omega also real and even. So similarly, the 14th real. Now it is a odd. So same concept we studied in the Fourier series. So x of t real, but it is odd. X of j omega now it is not real. It's a purely imaginary. Purely imaginary and odd. So note. So if x of t imaginary and even, x of j omega also imaginary and even. X of t imaginary but odd, then x of j omega will be real and odd. So 15th one, even and odd decomposition of real signal. So we know that x of t Fourier transform, it is x of j omega. So for the complex signal, so that is real part of the x of j omega. So real part of the x of j omega plus j into imaginary part of x of j omega. But in case of the time domain, so this is the sum of the even part plus odd part. So we can say that so even part of the x of t, so it is equal to the real part of the x of j omega. So odd part of the x of t, so it is equal to j into imaginary part of x of j omega. So this is the case. Last one, Parseval's relation. Already we studied in Fourier series. Parseval's relation. So this is the power relation between the continuous time domain and frequency domain. So first, left side is should write the time domain signal. So x of t equal to formula. So 1 by 2 pi integral minus infinite to plus infinite. So next x of j omega, take the mod x of j omega So this is the power relation then. So square. So mod of the exponential goes to 1. No need to take the that into d omega. Now write down the x of j omega formula. So integral minus infinite to plus infinite mod x of t square power. So power solution is nothing but power relation between the time domain, frequency domain. So the mod of exponential goes to 1 into dt. So, so this is the partial relation for aperiodic signal. This is for aperiodic signal. So these are the properties of the continuous time Fourier transform. We will do some more problems based on these properties in the next class. Thank you.